Oh putain, oh putain.
Hey everybody, welcome back. We're going to be doing another lesson in geology, this one on landslides and mass wasting. And these are the processes by which mountains die. At least it's one of the major processes. There's several other ways that it happens. We're going to get into those into future lectures. But the death of mountains can be spectacular. We're going to go ahead and lead off with the idea that landslides are a well-known geological hazard to many people. They kill over 4,000 people a year. They're a massive destroyer of real estate and personal investment. We have a great example of this in the image right here in front of us. Here we see a rock fall, a couple of rocks that came down this hill slope. This is in the Alps, this is in Italy. These rocks came down. We see one right over here. Turns out there's another one right behind the building. This rock has left a track. This is a vineyard that we're seeing here. It's come through the vineyard and come to rest right at this location. But before it came into this position, it crashed through this homeowner's garage. This is a 300-year-old home that has had the side of it completely wiped out. There's another boulder right on the other side of this. Fortunately, nobody was killed. The boulder that's right behind this building missed it by 2 feet. So it's just sitting back there resting. Is there any evidence that there might be a landslide hazard in the area? The answer is yes. Look at this boulder right here in the front. Turns out this boulder was not involved in this rock fall. It's a rock that had fallen some centuries prior, perhaps several thousand years prior. But it was out here in the middle of the vineyard. They built the vineyard all around it, knowing that it was here. Not sure what they thought that it was there for or how it got there, but they built it kind of ignoring the fact that there was this potential for a rock that could come right down the hill. So we have an unstable slope, we have evidence that it had been unstable in the past, and they built the house here anyway. Probably not the best decision that was ever made, but for 300 years it seemed like a great idea until it wasn't. And that's unfortunately the nature of landslides. Everything is fine until it isn't. And when it isn't fine, people lose their lives, real estate gets destroyed, and there's a lot of things that can go wrong. And that's what this lecture is going to be about. When mountains die and rocks fall. It's going to be interesting. I hope you enjoy it. Now, there's something that we have to accept when we are dealing with living on planet Earth, which is that slopes are everywhere. So slopes are very common in our physical landscape. They can be steep, especially if you have young mountain ranges that are rising up in your area. They could be moderate or they could be gentle, like what you see out in the middle of the Great Plains, whether you're in Russia, the United States, Brazil, or the Central Shield of Africa. They can be very, very flat. Some of these may be long and gradual, so long and gradual that it requires surveying equipment to see it, or it can be short and abrupt, like what you see going off of a cliff. Slopes consist of barren rock and rubble. We call those talus or scree, depending on the size of it and its location and context. We'll get into that here in a couple of slides. Or it can be covered by soil and vegetation. I have a great slide here that I found online, and I wanted to share this. This is a photograph that was taken by hikers on the Pacific Crest Trail in Washington. And in this image, we see both kinds of land surfaces. We see the vegetative soil area over here with the trees in the background, and in the foreground over here, we see these big boulders. Notice it's very angular. It's very large. This would have been a landslide deposit. We call this talus, by the way, so this is a talus slope. Notice that the slope is of a uniform slope. That's extremely important when we're looking for landslides and landslide environments in mountain ranges. So here we have a talus slope moving through here, covered in rock, and here we see the trail. This is the Pacific Crest Trail that we're seeing again in Washington State in the United States. So this is a typical slope that we would see that would be relatively unstable. We also know that this one's relatively young compared to the one in the background because there's no trees growing on it. The background has been around long enough for soil development to happen, tree roots to be able to penetrate into it. That's not the case here. This is a very young surface. And so it's also probably relatively prone to landsliding. Mass wasting, also called mass movement, and I will use both those terms interchangeably, by the way. Some teachers will refer to it as mass wasting, some as mass movement. I go back and forth between the two. I tend to kind of lean towards mass movement, but you can call it either one. Refers to the downslope movement of rock regolith. Regolith is something we described in our soils lecture, and soil under the direct influence of gravity. So this is not something where rainwater is washing the rocks down. That's a different phenomenon. When we get to rivers and waterfalls, we'll talk about that phenomenon, about how rocks are moved in rivers, because that's an extremely important part of a river. Not just the water, but the rocks that are moving along with it. But it's moving under gravity. So all of this happened because gravity pulled those rocks down towards the center of the earth. That's effectively what's happening here. The mountains rose up, and then the mountains are failing through these landslides and depositing rocks down these slopes. It occurs on varying scales. It can be very large, it can be very small, and speeds. It can go very fast or very slow, depending on the geological setting and environmental conditions. So if you are dealing with environmental conditions where it's dry, you're not going to get as much water. Water plays a major role. We're going to get into why it plays a major role. It's not what forces the landslide to move, but water can add a lot of mass, right? Think of a wet sponge versus a dry sponge. A wet sponge is much heavier than a dry sponge. So in terms of a desert versus a tropical environment, you're more likely to get landsliding where you have large amounts of water that can weigh down the Earth's surface. Now, we need to address the fact right up front that landslides are major geological hazards, which is one of the reasons why, it's probably the primary reason why human beings have such a keen interest in them. They're spectacular, as I described earlier at the beginning of the lecture, but they're also very ruinous to the lives of many people. It's very dangerous. A lot of people get hurt by them. They get injured by them financially. And it can be a major effect on commerce and national security for certain countries. I know that landsliding was a major event or a major factor that occurred during World War I and World War II when troops were fighting in the Alps, for example. This was a major problem. So a landslide is a sudden event where large quantities of rock and soil move down steep slopes. Now, it doesn't have to go quickly. Sudden could also mean unexpected in that sense. Now, when people and communities are in the way, a geological hazard may result. And when that geological hazard exists, people need to take notice because land always wins. Once something starts moving, something as large as a landslide starts building momentum, there's literally very little that we could do to stop it. And the best thing to do is just simply get out of its way. Now, the term landslide has no specific definition in geology. Geologists generally don't use the term. We use a more specific term like a rotational slump. This is a landslide, as the public would describe it. But a geologist would notice that this has certain features associated with it that would say, no, it is a slide. It's definitely a sliding event, but it's a rotational slide in this case. And it's defined by a certain rate of movement and the way that it's moving. And so we're going to go over the descriptions of each way those movements are happening. Now, this is a rotational slump caused by human activity. It's not an accident that it's occurred along this road. And in this way that we can kind of forensically put together a landslide, we can figure out what caused this landslide. In this case, it was the road construction over-steepening the hill slope back behind it. We can see that they've cut back this area here, but apparently they didn't do it enough. So this portion here failed. That's going to cause a large amount of damage. This is a hazard. Imagine running into the slope over here. You could go right off the road. People could get killed. This is something you have to be very careful about. So not only does landsliding have a major impact on our interest in natural hazards, but it also has a major impact on how we understand the growth and death of mountains. It's a very important thing. So first off, mass wasting, mass movement is the geological process that often follows weathering. So we described weathering in a previous lecture, the breakdown of minerals, the breakdown of rocks, and then the transport of that stuff usually winds up either under gravity and then eventually into the rivers. So ultimately, where does all that sediment wind up? That stuff that's broken up in weathering? It winds up in the ocean. Most of it winds up in the form of shales and siltstones way out in the middle of the ocean. Now, in terms of the combined effects of mass movement and running water, they tend to produce stream valleys. And of all the things on planet Earth, stream valleys are the most common and conspicuous of Earth's landforms. When people think about the Earth, the continents, we think of those beautiful rivers that are cutting across it, transporting water, silt, sediment, and all the growth that comes along with it in terms of the biota and the flora and the fauna. It's an incredible thing to think of, is that they're all tied together through these mass wasting events. Classic examples of this include the Grand Canyon in Arizona and the Punakha Valley of Bhutan. And so we're going to go ahead and show you some images here. First off, I want to show you some of the material that is being transported out of mountains that is part of a landslide breakup event. It's being transported right here downstream. These are large cobbles, boulders, rocks that are being transported under mass wasting events that have wound up in rivers. So it's being washed eventually out to sea. In terms of the Grand Canyon, this is something that is excavated largely by landslides. Even though there's a beautiful river at the bottom, you'll hear people say the river is what cut this down. Well, the river is partly responsible in the sense that this is, of course, being the Colorado River. The Colorado River has the role of transporting the sediment out of the area. That's the main thing that it does. And it does have the ability to erode and go straight down through the rock. Those are really important aspects of the Colorado River. But in terms of the rocks that we're seeing over here in the background, that's not because the Colorado River moved over into that area. That's because the rocks over in there fell off the cliff in landslide or a rock fall and wound up in the river, and then the river washed it out to sea. In the case of the Colorado River, it goes out to the Gulf of California in Mexico. So this is a very, very involved process. I want to show you the Punakha Valley where a similar process has happened. Now, one of the things I mentioned earlier is to keep looking for uniform slopes, and we see that here in the Punakha Valley. By the way, Punakha Valley is in central Bhutan. It's pretty much a part of the Himalayan uplift. So this is a very rapidly growing area. Its center river right here is transporting a large amount of sediment. In fact, it's choked with sediment. We're going to get into this in a future lecture. But when rivers tend to sidewind like this, it's called meandering, by the way. When it tends to meander like this, it tends to mean that it's got a sufficient amount of sediment so that it's starting to choke on that sediment. It's a very interesting process, and again, we'll get into that lecture. That's a future problem for a future day. But the point is that when you see uniform slopes like this, and you don't see any notches in here, those would be called fluvial terraces. When you don't see that in here, you can usually lay the blame for the formation of this on landslides. Effectively, the landslides are carrying the material down to the river, and then the river is washing it out. Because this river certainly doesn't have the capacity to burrow this entire thing out. There's actually very little evidence that that happened here. This is a landslide, for the most part, landslide-created valley, where the river has washed out the material that has made its way down to the bottom. So they're working together. Now we have to keep in mind that while mass wasting and mass movement are occurring, that's going to dramatically affect the landscape that we see. So most mass movement occurs in areas that are rugged and geologically young. So those young mountains that we were describing in the last lecture, those are the areas where we see the largest magnitude of landslides and mass movement. The Himalayan mountains, for example, are a classic example because we see very, very steep slopes. So here's the Himalayas. Here we see it here. This is a photograph taken from a bus where it shows how steep everything is, to the point where they actually had to excavate right into the wall of the cliff to be able to get down this river valley. It's an extremely dangerous trek, and so this is a phenomenal picture to get. So as mountain building subsides, as it slows down, mass movement and erosional processes tend to lower the land. And so you get the Himalayas like this will turn into mountains more like the Appalachians. We described before that those are both collisional mountain events, or collisional continents where continent on continent collision occurred. The mountains were probably of similar heights. And so over 500 million years, the Himalayan mountain ranges will eventually erode down and look like the Appalachian. Notice that the slopes are gentler in the Appalachian that we see in the Himalaya. It's a very, very different slope that we're seeing there. So steep and rugged mountains eventually transform into gentler, more subdued terrain. It's the landslides that make this happen. Okay, anything that falls off of here is going to wind up in that gully. Anything that winds up in that gully is going to get washed out by that river. Landslides are going to be pretty dramatic in this environment. In terms of controls and triggers for mass movement, there are several that we need to keep in mind. These are responsible for far and away almost all of the landslides that occur on planet Earth. There might be occasional other ways that they can form, but this is the way that they happen naturally. First and foremost, gravity is the driving force of mass movement. It's just gravity. Anything that has any type of involvement other than gravity, it's a different process. So long before a landslide occurs, various processes work to weaken slope material. It could be the removal of vegetation. It could be the destruction of minerals through weathering, whatever it is. And during this span, the slope remains stable but gets closer and closer to being unstable. In other words, it can hang out there for a very long time, be stable, be functional as a shoulder slope to a mountain, and then one day it's not enough, right? There's going to be a trigger. So eventually a trigger occurs, which is an event that causes the slope to become unstable. So it goes from stable to unstable. And here we see a slope where this has happened, right? Vegetation everywhere is nice and it's uniform, and then all of a sudden this thing failed. And unfortunately, this killed over 100 people. This was a terrible mudslide that occurred, but this is a slope that failed. And this was associated with one of the causes we see here. It's this first one, saturation of material with water. We'll get into why that happens here in a little bit, but if you get the right conditions, horrible things can suddenly happen, unexpected things can suddenly happen, and you can see that this community, which was all along here, was buried. There's homes underneath here. They're now buried, and unfortunately there were people killed. So you can trigger a landslide through saturation of material with water. This was caused by a series of storms, in fact. Oversteepening of slopes. So if you cut into a hillside, for example, to build a road, you provoke that mountain to start to slide down. We'll show you why that is in the next couple of slides. Removal of anchoring vegetation. Sometimes it's the trees and the grasses that are holding everything together. You remove that stuff and things start to fail and slide. And of course, ground vibration from earthquakes. This is actually a major trigger for landslides. In fact, I'll show you a it's an amazing photograph taken of, unfortunately people were killed in it, but it's an amazing photograph of a landslide in Japan that was triggered by an earthquake. In fact, the entire region shook violently, and the result is phenomenal photography, but horrific effects because, like I said, many people lost their lives. All right, so I want to talk about the role of water in landslides. This is far and away probably the number one culprit for the creation of landslides in unexpected areas. So first off, water adds weight to a mass of material. It's like a sponge. Like the Earth has pore space. The soils up here have that we're seeing in this one. This is a landslide here. This is La Conchita in California. This is a very, very famous landslide. Unfortunately, people lost their lives in this landslide. But effectively, the La Conchita landslide was provoked by a large amount of water that got into the soil. Now, where the water came from was a matter of major litigation and controversy, and we'll talk about that here in a moment. But at La Conchita, there were several landslides that had happened here. So first off, there was one that happened in 1995. This was a landslide. This is the top of it here. It used to be all the way up here at the surface. It has dropped down, and that landslide here came down in 1995, and nobody lost their lives. This was a coherent slide, kind of like dropping like a block of land down. It just went from high to low. And in fact, there's an ancient landslide. We could see it where it started to slide, but it didn't come all the way down. And here's the scarp for it right here. So this bench that we see up here was originally matching this land surface up here at the top. And it slid down over here. So this area here is not terribly stable either. And of course, where are people living? Right here at the bottom. This is not a smart place to build homes, if you ask me. In 2005, there was another landslide called, in this case, it was called a debris flow. We'll get into what a debris flow is here in a little bit. In this case, the debris flow was a failure that happened here, and instead of it coming down as a consistent block, a consistent landmass that dropped down, the debris flow was a mass of earth and water that came down into the neighborhood and covered this entire area here. And there were 10 people killed when this event happened. In terms of the source of the water, there's definitely storms that were playing a role that provoked or triggered this. But there's also a concern with this orchard that we see up here up on top. And I believe it's an orange orchard, if I can recall. And there was a concern that this might have been provoked in part by improper drainage being used by the person that owned this orchard up here on top when they were watering the trees, or they were using some type of water catchment system, that the water was leaking down into the slide. And so the slide was artificially already wet by improper drainage practices being used by the person at the top of the slope. So when the storm did finally hit, it basically was the trigger that normally wouldn't have happened, but it triggered a slide, a debris flow that wound up in the deaths of 10 people. So this land up here is now, was forfeited by the landowners in some type of major settlement. But it's a total tragedy that this happened at all. People shouldn't be living in an area or building in an area, in my opinion. This is right next to, of course, here's the Pacific Ocean. This is the beach right here. The riprap is right here. So this is the Pacific Coast Highway. The Pacific Ocean is just a few feet below this image. So the reason why people live there is the ocean. But the reason why people are dying there is because of the landslide. It's a very, very dangerous place to own land. And the reason why this is happening, by the way, is because of the amount of weight that the water is adding to the soil. So let's look at what water does. So water does a couple of things to sand, soil, silt, clays, the sediments that make up many of the sliding surfaces in landslides. So when sediment pores fill with water, there's cohesion amongst particles, and sometimes the particle cohesion can be destroyed. So if you have dry material like we see here, there's no cohesion at all. The water isn't connecting. First off, water has hydrogen bonds. It creates surface tension, and it makes things sticky. So once you have dry soil, perfectly dry soil, it just kind of acts like grains. It doesn't have a whole lot of cohesion, and it'll form a pile, but the pile is entirely based upon something called the angle of repose. We're going to get into that in the next couple of slides. That's what controls how tall things can get in a dry sand pile. But once it gets wet, or I should say moist, this is to say where that's partially wet and partially dry. So in other words, these cavities have air as well as water. Then all of a sudden there's cohesion, and you can make things like sandcastles. Things stick together. The reason why is these little grains start to act like magnets almost, the way that they stick together. Now, once you get full water and you fill in all that airspace and there's nothing but water inside that pore space, then it becomes saturated. And once it becomes saturated, or even super saturated with water, where there's so much water that the grains float apart, the grains no longer are cohesive, they don't stick together, and they start to flow like the water. And so here we see on a beach, here's a wave that's moved through, and the sand is now flowing just like it's in the water. So we can go from no cohesion to good cohesion, and then the thing begins to act like a fluid. And so when we have water saturation that happens back over here at Lock and Cheetah, we believe that this is what happened here. Because effectively it hit saturation and the entire slope failed and catastrophically formed a debris flow that went downhill. Another way that we can trigger landslides is through oversteepened slopes. There's many, many geological environments where this happens. There's these things called couloirs. So this is a couloir right here. I'll describe what that is here in a moment. Stream valleys and human activities can do this. So a couloir is effectively a high angle valley in a mountain. A couloir is, so we could think of a mountain like this, or I'm sorry, of a valley like this, and then a couloir is just something that's at a high angle. So it's coming down. These are really well studied and well known because they're used for skiing a lot of ski resorts are built around couloirs. So we have a lot of debris. You get glaciers that sometimes come out of these things. They're impressive events when they're formed and when they have avalanches and things like this. We're going to talk about avalanches actually also in a couple of slides. So a couloir, a stream valley. In this case, the stream is coming through and undercutting and oversteepening this valley here, this canyon wall here. And so when it oversteepens, of course, gravity is going to do what gravity's going to do. It's going to pull it into the bottom of the valley, and you're going to have slope failure. Same thing is happening here, oversteepening, despite the fact that they put the fencing up over here to try to hold back the landslide. The landslide is just too strong and too heavy, and it broke through and went out onto the road. So oversteepening slopes are going to give you landslides. And so you do get landslides. There's a huge amount of debris and material that comes down this way. The only reason why it's clean is because the snow actually occasionally generates avalanches that keep it clear. So there's going to be a large pile of material at the bottom, but this is an interesting couloir. There's famous couloirs across the world, again, used for skiing, but it's also where avalanches happen. So there's a reason why avalanches and skiers tend to happen at the same location. They tend to like the same locations. All right, so let's get into the reasons why oversteepened slopes are a problem. And in order to understand that, we need to understand something called the angle of repose. So unconsolidated granular particles, like that pile of sand I was showing you earlier in the hands of that person right here. So right here. Okay, that would be an example of granular particles assuming an angle of repose. So the angle of repose is the steepest angle at which material can remain stable. And it's different for various materials. So if it's fine sand, it's usually about 35 degrees. So this would be the angle here. And you can have a 35-degree angle, and you can pile up fine sand and have it nice and stable like that. For coarse sand, it's about 40 degrees. For angular pebbles, it's 45 degrees. Now, if you add to it the idea that it's either moist, dry, or water saturated, you get very different angles, right? So this is assuming that you're going to get dry fine sand, dry coarse sand, dry angular pebbles. But here we see it dry, moist, and wet. So water plays a major role again in terms of the cohesion of these dry particles. Now, why is this a big deal? Well, we can imagine that we have a slope angle of less than the angle of repose. So even if it rains, as long as it doesn't hit saturation, the angle will be stable and this won't fail. But if it's at an angle greater than the angle of repose, in other words, the stable angle at which everything works, what will happen is mass wasting will happen. The slope will fail and there will be a landslide. Material will move down the slope face. Here's another example of what we're talking about when we've oversteepened. So we can imagine that we've got this angle of repose that's set right here, that's indicated by this line here. That angle of repose is being violated because we've modified the slope. Let's say we built a road here and this is a hillside. So by doing this, what we've done is we've now kind of provoked a response. The angle of repose is being violated. Just like we're seeing over here, the material is going to come down and fill that hole. Same thing is happening here. Effectively, a slide slump or free flow deposits are going to come down. They're going to fill this gap in the angle of repose. They're going to fill it up, and it's going to create rock slides to make this happen. And eventually it will stabilize. So the Earth is kind of constantly self-annealing whenever there's a major violation of this angle of repose. Oversteepened slopes are unstable and can trigger mass movement. Another crucial trigger is the removal of vegetation. So plants protect against erosion by binding the soil and regolith together using roots. This is a major functionality of vegetation in mountain ranges, is as long as you have good forests, good grass, and things like this, you have fairly good protection against certain kinds of mass movement. But if you have some type of mass removal of the vegetation, let's say through a forest fire, or by humans doing something foolish like farming or some type of development that completely wipes out the timber in the area, you can get fast-moving debris flows that can be extremely destructive. A classic example of this happened in Montecito, California. This is a debris flow that happened after a wildfire. So the vegetation was completely wiped out. There was nothing binding the ground together anymore, so the angle of repose suddenly was no longer valid. And as a consequence, a massive amount of debris after a huge rainfall came down and deposited into the valleys and gullies down below, and results in, I mean, you can see it. It's a huge debris flow. Landslide, huge blocks of material, roots, tree material. I mean, the entire mountain came down. This was an extremely deadly event if you were caught in it. Okay, so the last kind of trigger that I want to talk about is going to be earthquakes as a trigger. So earthquakes and aftershocks can dislodge rocks and unconsolidated materials. That's kind of self-evident that that's going to happen, but the magnitude to which that occurs is kind of alarming. People don't usually anticipate the amount of damage that can come from a landslide that's triggered by an earthquake. You would think it would just knock down some rocks and things like this. They can be massive, massive, massive events. So I want to give an example for California and for Nepal. In 1994, the Northridge earthquake, which was an earthquake I actually experienced, I remember going through it, it triggered 11,000 landslides in the area, and it did a lot of damage to a lot of properties in the area. In 2015, a major earthquake happened in Nepal, and it triggered thousands of landslides, and in this case, 8,900 people lost their lives. This is an example of a place that lost their life where there was a photograph taken beforehand. This is the village where people were living, and then the landslide came through, and again, fatalities are here. This is a mass grave at this point. It's an extremely deadly event when earthquakes trigger landslides. One of the reasons why, of course, is liquefaction, which we talked about in our earthquakes lecture. So liquefaction is during periods of ground shaking, water-saturated surface materials, there's that word water-saturated again, behave as fluid-like masses that flow, and that can cause things to fail and become extremely destructive. All right, so now that we've gone through the triggers and we have a good idea of what it is that we're dealing with here, let's go ahead and jump into the classifications of different types of mass movement, the different kinds of landslides that are out there. So there's two things to consider in terms of processes. There's materials and there's the motion, right? So it's what it's made of and how it moves. Those are the two things that we need to take into consideration. So in terms of types of material, there's debris, mud, and earth, and those are all used if soil and regolith move. So you would have a debris slide, a debris flow, things like this, a mud flow, an earth flow, things like this. We use the word rock in the term if bedrock is moving. So here we're looking at a couple of examples. This is something called a lahar. A lahar is a volcanic mud flow. This is one that happened in Indonesia. Came through this area, extremely deadly, by the way. Lahars are some of the most deadly phenomenon on planet Earth. And then here we have a rock slide. This is in Idaho. This is something that came down the mountain, extremely fast, high velocity. Again, this is bedrock that's moving, extremely deadly event. So earlier I mentioned two different substances, and I said we'd come back to it, talus versus scree. So it turns out that whenever you create mountains and you have any kind of weathering, there's going to be rocks and pebbles and gravels and stuff distributed all across the surface of these mountains. And that's just because of weathering. So you get loose rocky material all over the place. It accumulates on the surfaces and it starts to get involved in the mass movement processes. And eventually it can be part of a landslide. So loose rocky material formed by weathering on slopes is generally called talus or scree. In fact, scree is a more common term used in England. It's less commonly used in the United States, and then of course other countries, Australia, Canada, they use variations. Some will use talus, some will use scree, depending on the on where the professor takes a larger amount of their experience from. And there's no formal definition between the two that exists in geology, right? I mean, you'll frequently hear the terms used interchangeably, but I will say that this is just from my own experience and from talking to others. Typically, scree is a term that is used for gravel-sized material or smaller on a slope. So in theory, you can ski on a scree slope. And so this is something that people do. Here's in Austria, this is somebody scree skiing. This is a little bigger than gravel. If it's gravel, it's very, very large, coarse gravel. But in other words, you're able to go through it and it'll move out of the way. This is a lot different than how we usually think of talus. Talus is typically used for cobble-sized material and larger that has moved in a fall. So in other words, scree is usually the stuff that's already kind of just sitting there. It's the rock fragments that are just sitting there from weathering products. Whereas talus is usually defined as something that has already been involved in a rock fall, but it's large and it's large blocky material. And again, this is from my own experience. There's no formal definition, but I'll use those two terms in that way. So scree is usually the small stuff, and talus is the large blocky stuff. So this would be talus, and this would be scree right here. All right, so let's get into the types of motion now that we've talked about talus and scree, because those will be terms I'm going to be using a few times in these next couple of slides. So a fall is the free fall of detached pieces of rock, and that's called a fall. Okay, so talus and scree slopes and talus cones, so here we see talus cones in Norway, are built by rock falls accumulating at the base of cliffs or slopes at the angle of repose. So here's a diagram that kind of explains this. You'll have a cliff. Here's the angle of repose of the talus. This is an unstable cliff. It's obviously going to be unstable when you have that type of angle. Any material that comes off is going to fall down into the talus pile down below. So here we see the talus slope or the talus cone that is forming. It's going to take on that angle of repose. And here we see that beautiful angle of repose right here. It's uniform across this entire surface here. Here's another one. Again, talus slope with the angle of repose forms a nice talus cone. So the next type of motion that we would have rather than a fall is going to be a slide. And it turns out there's two different kinds of slides that are prevalent on planet Earth. So a slide occurs when there is a distinct zone of weakness separating the slide material from the underlying material. In other words, there's a zone of weakness, they're in contact and they're moving, whereas a rock fall, they come out of contact with one another. There's actual air between the two. Okay, so there's a translational slide. This means the material moves along a flat surface. So here's an example of a translational slide. It used to be attached here, and this is the original position, and now it's moved into this new position here. And so the tree doesn't even know it's moved in this case. The rock is moved, but the tree is just kind of going along with it. In a rotational slide, there's actually a curvature that happens here. And this is pretty common. This is actually a lot more common than I think people realize. And the surface rupture tends to be concave up. In other words, it comes out here to the point where there's this end that comes out of the ground. So this goes into the ground, this comes out of the ground. It rotates in and out. This is called the toe. This is called the head of the slide right here. And that's called a rotational slide. And so here's a giant rotational slide. Here it's dropped down here on the top. This is the original position. It's dropped down. See that's happening here. And so down below there's a toe that's coming out somewhere else. This is a massive landslide in Peru. Now, when you get material that starts moving and breaking up and starts behaving like a fluid, it's called a flow. And so the definition of a flow in this case occurs when material moves downslope as a viscous fluid. Most are saturated with water. There's a lot of water usually involved. And so the water starts to separate out. It's basically a liquefaction or a liquefied material that's undergoing liquefaction while it's moving. It's pretty interesting stuff. It has a lot of different physical features, and there's a lot of science behind it. This will funnel into stream channels, I said canyons, will entrain most objects they encounter. To entrain means to pick up and to carry with it. So if you happen to be in front of a flow, like a debris flow, you're going to become part of the debris that's in that flow. There's no getting out of it. These things tend to be extremely dense, in fact, twice as dense as flowing water. The reason why is because you got rock mixed with water that's moving. That's denser than just pure water. This is one of the reasons why people and objects and things that get caught up in these debris flows or in any of these kinds of mud flows or whatever it is, have no ability to get out of them. They're completely trapped in them because you float like a cork. You have no control over it. The average density of the human body is nowhere near twice as dense as floating water. In fact, you're about as dense as water, roughly. So you have no control over the environment. And as a consequence, things can get extremely destructive, extremely deadly. Imagine having your house getting impacted by a debris flow that is twice as dense as water. I mean, just even getting hit by water would be destructive. Now imagine twice as much mass in the same amount of volume of material. Yeah, it's completely unsurvivable. It's a totally unsurvivable event. That's the reason why these flows are so destructive and so deadly. I'm going to go back to those deadly events I was mentioning earlier. You'll notice that they were both flows. Let's go back to this. Here we see a debris flow. Right here, this is at La Conchita. This is the one that killed 10 people. It flowed all the way out here into this neighborhood and killed. The fatalities were, I believe, all right in this area right here. And of course, this one here in Guatemala, same thing, over 100 people. This was another mudslide. This was a flow that came through here. So this is extremely destructive stuff. Lots of water was involved that allowed that to break up and to behave in a way that was different than, say, a standard slide like we would see. So let's see if I can find it right here. A translational slide, which is destructive enough. But when it breaks up, I mean, it becomes completely uncontrollable, and it can go very, very long distances within these channels. Just to give you an example, or to give you an idea, these are giant boulders. I mean, these are boulders larger than than well, I wouldn't say larger than a car, but they're in the same neighborhood, right? These are really, really large blocks, and they're floating like corks inside this material, and they just get swept right down the mountain. There's nothing that can stop these things at all. The only thing you can do is hope that it stays within the channel, that it doesn't get out of the channel and cause a lot of destruction. All right, so there's two different ways that they move in terms of velocity. So they can move very fast or they can move very, very slow. And there's a wide range of things that happen between these two, right? It could be intermediate. Now, the fastest ones, of course, are the rock avalanches. And a rock avalanche is the most rapid type. The rocks actually float on air as they move down slope. I mean, it's kind of crazy how far these things will go. They'll go very, very long distances from the hill slopes from which they originate. Or they can go extremely slow. Something called creep moves particles a few millimeters per year. So here we see the examples of material that is coming through. These are rockfall fragments that are moved quite a bit a ways away from their original source, which is up here. And here we see soil creep. This is what's happening because as the top part of the soil, the surface part of the soil, is moving down slope, but the roots are down below where it's not moving, so the trees are constantly being rotated by the upper layer of soil, so they have to bend like this to stay upright. Otherwise, they'd all be turned over like this. And so these are trees that are showing that the soil is slowly flowing downhill in this direction. And so the trees are bending to stay upright so that they can carry out their standard photosynthetic processes for life. Okay, so now that we've covered the criteria by which we classify different types of mass movement, I want to go ahead and start covering the rapid movement types, whether it has rock or debris or anything like that in there, and show you what that looks like. And let's start off with probably the most famous types of landslides, which are rock slides and debris avalanches. So a rock slide occurs when blocks of bedrock, remember we talked about the word rock had to be involved, so if it's got the word rock involved, that means bedrock is involved. So break loose and slide down a slope. This is a very, very major event when this occurs. A debris slide occurs when unconsolidated material slides down a slope. So this is a rock slide with rock. Debris has the blending. And after the initial sliding stage, material can break up into a debris avalanche. In other words, it could become disaggregated, break up in the entire sliding block, break up and tumble down the slope. It could even catch air to some extent and go very long distances. They're very, very fast. They can go at speeds far exceeding 100 miles an hour. There's simply no way to get out of the way of some of these things. They're just extremely destructive and completely unsurvivable events if you ever get caught in them. So here's a rock avalanche deposit in Washington. This is, again, the forest that's here has been completely wiped out. So if it could do that to a tree, imagine what it would do to a human being. It's completely unsurvivable. And it's a huge amount of material coming down. So, you have enough of these coming down, you can wipe out a mountain pretty quickly. this whole slideshow is about the death of mountains. And so this is effectively what we're seeing is the material being shed down from high elevation in those mountains on down. So that moves us over to debris flows. So a debris flow is another extremely rapid form of mass movement that involves the flow of soil and regolith with water. So it's a mud flow if the material is fine-grained. If you remember when we were talking about mud is being defined as silt and clay when we talked about sedimentary rocks earlier in the lecture series. They tend to occur more frequently in semi-arid mountainous regions, and we'll get into this here in a moment. They are usually the result of sudden rainfall. So you would think, well, saturation should be a major issue here. If you have, if you have a dry area and it gets a little bit of water, what's the big deal? Why would that cause a debris flow or a mud flow to kind of suddenly show up? And the main reason is not only do we have large amounts of water that might come in, but you have a lack of vegetation to anchor the soil, right? So an arid environment, think of like a desert or a semi-arid environment. It's going to get a lot of water, but maybe not a whole lot of vegetation to hold things together. Suddenly things are going to start moving, they're going to start flowing, and that's what we see in here is a debris flow deposit that came through this area here in Arizona. This is Fish Creek, Arizona. This is a photograph from the United States Geological Survey. And the material started over here. You get a lot of rain, and it'll just kind of come out and spread out. And that's what we're seeing here is one of these channels, for instance, up in here. And you see huge amounts of material that just suddenly washes straight out. So you have huge amounts of sediments in the rivers, and it often is confined to channels and canyons. So it's again another. If you're in this type of environment when a debris flow comes through, it's unsurvivable. This material here is big, it's blocky. It'll pick you up like a cork. It'll toss you and it'll crush you between the boulders within its flow. So it's an extremely dangerous and unsurvivable event. All right, another rapid form of mass movement, an extremely deadly landslide or mudslide type of event is a lahar. And when you can't say the word lahar, not immediately just kind of shudder when you know what these things do. They're exceedingly deadly, exceedingly dangerous events when they happen. So a lahar is a debris flow that is composed mostly of volcanic materials. An example of this would be Mount St. Helens. This is a photograph of Mount St. Helens with a lahar coming off of it. Lahars are extremely unexpected events when they happen. They do not require rain to happen. Effectively, when a lahar occurs, it's usually because the volcano heats the snow cap on top of the mountain unexpectedly, and then a massive volcanic flow comes running down, and it could bury people alive. Entire towns in South America have been known to completely disappear, with tens of thousands of people losing their lives in a night. They're extremely destructive and frightening. Historically, some of the most deadly volcanic hazards are lahars. Whenever you look at maps of where lahar deposits are, you should take them very seriously if you live near a volcano. I do know that major cities in the Washington area of the United States, for example, when I say Washington, I mean Washington State, are resting on very recent lahar deposits. So this is something that people need to take into consideration when they're thinking about buying a home or where they're going to raise a family, is can you get out of the way if in the event of a lahar? You don't need a volcanic eruption, like I said, to get one to kick off. So they're dangerous. They can occur during a volcanic eruption or even when the volcano is quiet. They take place when highly unstable layers of ash and debris become saturated with water. Effectively, it makes a slurry, almost like a concrete. It's extremely dangerous stuff if you ever get stuck in it. And it generally will follow stream channels, which you would think, well, that gives you some degree of safety, except for where do people like to live? Well, they like to live near the streams. It's a pretty common thing. So here's a couple of images again. Mount St. Helens right here. Here's that lahar. Here's the lahar coming through. It's burying this property here. And that is responsible for many of the deaths that occurred during the Mount St. Helens eruption, which killed roughly 50 people. These are the kinds of events that when people go out and study lahar, like I said, geologists immediately shudder at the level of destruction that a lahar can do. And it's generally misunderstood by the public how dangerous these things are. What I wanted to do in this lecture is also bring in the idea of a snow avalanche. Most geology textbooks don't cover it. In fact, the geology textbook that I generally use in my classes covers snow avalanches by not even discussing them, not even at all. And the reason why is because they don't usually involve a whole lot of rock. But the physics is exactly the same. They're extremely important, and they do fit a certain categorization of being an avalanche. So I want to talk about snow avalanches. While they don't move a whole lot of rock, they can move some. They're usually treated as a secondary cause of erosion and weathering and mass wasting for rocks and the cycling of the rock cycle. But I'm going to go ahead and cover it anyway. Two quick slides, just a little bit on snow avalanches. So a snow avalanche is also called a snow slide. It's a sudden release of snow and ice from the mountain slopes. Now, we haven't talked about the origins of snow and ice. We'll get into that into a later lecture. But it's something that I think plays a major role, certainly in the formation of couloirs and things like this. So I like to cover them. Sometimes these avalanches will contain rocks, soils, and vegetation if it picks it up. So the angle of repose for granular snow, this is snow that just falls out of the sky and falls as flakes onto the ground, is about 38 degrees. So an angle of anything greater than 38 degrees is going to fail. So that's the reason why that's an important number. Those snow slabs may slide on angles as low as 20 degrees. This is a theoretical number. It turns out that when they go out, they study or they observe, most snow slabs will actually slide at 30 degrees. So a snow slab is a translational slide of snow. Imagine a snowpack, and the whole snowpack just starts sliding rather than it moving like sand and tumbling down, which might happen. The main thing is it moves like a translational slide, and then it'll break up as it moves. And that's the reason why it's called an avalanche. Same thing as a rock avalanche, right? The rock avalanche will be a coherent block of rock that then will break up and start to move down the slope. So snow avalanches begin on snow-covered bedrock slopes of typically greater than 30 degrees. This is what we call the starting zone. It can occur as low as 20 theoretically, but it's observed at over 30. So that's the reason why there appears to be a discrepancy, by the way. So theoretically, it could be as low as 20, but 30 degrees in the Alps is where most of the studies are done, show that that seems to be the magic number. You get over 30 degrees, you get avalanches. As the avalanche travels downslope from the starting zone, so this is an area of greater than 30 degrees, it'll come down the track. So here we see a track. Here's a couloir right here, in fact. So its movement is either confined to a couloir or valley or unconfined down an open slope. So this is where it's confined. It's coming down a couloir. These are little couloirs right in here, but there's the main one coming down here. And it runs all the way down to the bottom. And the avalanche will begin slowing and depositing on slopes of less than 15 degrees. We call that the run-out zone. So the material over here is at 30 degrees or greater in terms of the bedrock, right? So the snow is pretty flat, but the rock underneath it is actually at a pretty good angle. So material will break loose, come down the track, and then deposit down here in the run-out zone. And the speed of movement depends on the level of water content and ice density. Does that sound familiar? Yeah, just like landslides, right? The density of the material and the amount of water plays a major role on how far and how it all moves, right? Whether it's going to be a flow or whatever it's going to be. So that's the reason why I have it in here, because it does have a lot of very close parallels with the way that landslides work. Here we see a couple of images of snow avalanches. The one up above is something called a powder snow avalanche, and the one down below is called a wet avalanche deposit from what they call a flowing snow deposit. So where do we get avalanche terms from? Well, you look at a chart like this. This is from UNESCO, which puts together charts like this for public safety. And so if in the origin, which is say the areas of greater than 30 degrees, let's go back here. So here's the origin. Here's the transition or the track, and here's deposition. Oops, sorry, I moved ahead. Here's the depositional zone or the run-out zone. So if it's up here, it's the manner of starting here, the position of failure, the liquid water and snow, if you take these different things into consideration. So if liquid water is present in the snow, let's say it's snow, but it's rained on the snow, so it's present, then you've got a wet snow avalanche that might start forming up at the top. And as it transitions down, we can look to see how it behaves, and in this case, we see a whole lot of mixing of air along with the snow. That's why it's called a powder snow avalanche. This is where we see snow dust that's moving as a cloud down the slope. Down here, we actually see it's a wet avalanche. It's all moving as a wet avalanche deposit. So this is a wet avalanche deposit from a flowing snow, which is located, where do we got our flowing snow from? I seem to have lost it. Here it is, flowing snow avalanche. So this moved down the track and then it deposited itself down here as a wet avalanche deposit. So they're extremely dangerous. People lose their lives all the time. They're extremely dangerous events, and they can go at speeds of as large as 200 miles per hour. They can be completely unsurvivable, just like you see in a rock avalanche. Occasionally, if they carry material with them, and this is the reason why I'm incorporating them into a geology lecture, rather than just something that's more akin to what they call geomorphology, or something that studies surficial processes and its relationship to the environment, is because it can become contaminated. In other words, it can carry rock debris, soil, branches, trees, things with it down the slope. And in fact, we do study avalanche deposits along hill slopes and mountain slopes in largely alpine environments where we can see big boulders have been translated or transmitted by avalanches long distances. All right, so moving from avalanches and flows into slumps. So a slump refers to the downward sliding of a mass of rock or unconsolidated material that moves as a unit over a curved surface. It does not tend to travel fast or very far, but it's not slow either. It's something that will happen over a couple of hours, maybe a couple of days, but it's relatively fast. It's not creep, which can move, a few millimeters per year at most. So here we see a typical slump. This is a slump with what we call a head scarp. So the scarp, if you remember when we talked about faults, the scarp is where the rip in the surface of the earth occurs. So here we see that right there. And at the base of it is going to be an earth flow. This is where the toe of this rotational slide is going to come out. And so here we see that zone of rupture, and here we see the earth flow. And that's what this is right here. So we have a zone of rupture. This is seated into the earth almost like a chair, and it's being rotated out. And that's how these things work. It tends to do huge amounts of destruction. These are called slump blocks right in here. This is a relatively small one, but it's a great photograph of it. But they can be very, very large. Another one is a earth flow. Earth flows are relatively fast. They tend to form in humid regions, especially if you have large amounts of precipitation and snow melt. And they commonly involve materials that are rich in clay and silt, so fine-grained stuff. It's very viscous. It tends to move at slower rates than most fluid debris flows. It can happen overnight, but it kind of comes and it's sticky and it's a very interesting phenomenon. This is one that we see from Northern California, just north of San Francisco. I believe this is in Marin County. This is an earth flow that we see here. There's a couple of areas, a couple of little head scarps, but the material is now moving through, and it's just the superficial stuff that's moving right at the very, very top. So this is caused by, it turns out, large amounts of rain that is weighing down that superficial material, wetting it, and changing the composition of the clays, or the consistency, I should say, of the clays, so that it is more likely to flow than it would be if it was dry. Sizes range from a few meters to more than 1 kilometer long and several hundred meters wide. So here we see another one here. This is just a little earth flow. This person here is standing on the end of it, the very foot of it. But here's another one again. This is a very, very large one on this hill slope. All right, so now let's transition from what we would consider fast, so even those earth flows were still considered relatively fast, to very slow. Let's go to the slowest one, creep. Creep is the one that people don't expect to ever have happen, but they notice it over very long and prolonged periods of time. So creep is the gradual movement of soil and regolith downhill or downslope. It's imperceptibly slow. If you were to go outside and look at it every single day, you wouldn't even notice it. There would be nothing that would catch your attention. You wouldn't notice suddenly a stick moving over or anything like this. It's completely imperceptible. aided by the alternate expansion and contraction of the surface material. So effectively, this is the idea, is that you have bedrock with soil and regolith sitting up on top of it. And then above that, you have a surface, when it's frozen, that elevates, lifts, elevates and lifts, and moves things along. And effectively, these little pebbles, or the material that's at the very surface, kind of walks almost the same way that you do when you're ice wedging, right? Freeze, thaw, tends to expand, contract, expand, contract, expand, contract. And so you get a physical process that is breaking up rocks in ice wedging. Well, we're seeing something similar happening here, except instead of the wedging manifesting in the breaking of rocks, what it's doing is it's manifesting itself in the creeping of the soil. So the soil will expand up and drop down according to gravity, because gravity will pull it straight down. So it'll push out, down, push out, down, push out, down, and it will cause the overall soil to creep down gradient, down the slope. And you'll see this mainly in fences and utility walls that will begin to start to tilt. So this is a fence line that's clearly tilting. Here's some utility. That might be an old power line or telephone box. I'm not sure exactly what that is. But here we can see the telephone poles are clearly all being rotated. And this is due to the creep. So it's just simply rotating everything along. Solifluction is another way that we can get soil to move in mass amounts very, very, very slowly. And this is usually more common in waterlogged soils in very, very frozen areas, in very cold areas like Alaska, northern Canada, Siberia, places like this. So it's the downward movement of waterlogged soils. It literally means soil flow, and it's promoted by a deeper, dense clay hardpan or impermeable bedrock layer. So if you have permafrost or a bedrock layer, something that is really, really hard, what will happen is that it'll stay in that position. And then the material, the upper layer that heats up or warms up during the daytime, will actually start to flow down gradient or down slope. So, here we see permafrost. So, commonly in regions underlined by permafrost, it occurs in the active layer, the zone above the permafrost. So the active layer is this top stuff. It's the stuff that's moving. So if we look at this image here, we can see these lines. That's where we see these lips of slides that are moving. And they'll kind of crawl over one another, place to place. In fact, that seems to be happening right up over here. So they'll do this, they'll catch up with one another, and what they'll do is they'll build up these little lips, or what they call a lobe, a solifluction lobe. And what'll happen is, as this active layer crawls over previous material that is slid, that previous material that is slid now is insulated to the cold, and it freezes. And so now that becomes the new frozen surface, and so the active layer then moves out across it, and it builds up a lobe at the end. And that's what we're seeing here. This is that lobe. Here are those lobes right there. And this is all material that over a long period of time is transporting a huge amount of material down slope. Eventually it's going to wind up in a river. But that permafrost is going to be there and underlying all of this stuff, and that is eventually going to get involved in some of the processes. Now, you might be one of those people that are out there watching this video that might be living in an area that is subject to landslides, that they're just all around you, that there might even be affecting your property, and you might be watching this video just because you want to learn about the phenomenon. What can you do to learn about it in terms of detecting them, monitoring them, and getting them to stop? And there's different things that we could do in terms of techniques, and geologists use them all the time. And successfully, we do sometimes stop landslides from happening. But we have to detect them in the first place, which is the hardest part. So active landslides of all types present serious risks to human life and property. And it's a very serious risk. Detecting a developing case of mass movement can, 1, save lives. It can permit real-time monitoring of the situation. It can trigger effects to diminish the threat, what we call mitigation. And there's different ways that you can mitigate a landslide. For example, you could put pipes or whatever into the landslide and drain the water out to remove some of that mass that might be building up and causing it to slide in the first place. There's different things that you can do, right? Field mapping of ground deformation is used to detect potentially active landslides. I'll actually show you where field mapping has shown actual tears in the surface of the land. right where the headscarp is beginning to develop. And so the kinds of things that you might see where there's an active landslide investigation going on is something like a slope slope movement sensor. So here we have basically a connecting rod. Here they're putting it through a pulley, but effectively you have a rod that goes through a pulley and that is connected to another rod on the other side of the slide, and then effectively you see if the two are pulling apart, and then you can measure the rate at which it's moving. You can measure what they call the pore pressure. The pore pressure is the amount of water actually exerting pressure on the grains within that slide. So the pore fluid pressure is an important part of what might motivate a slide to move. We didn't get into that in too much detail except to talk about the cohesive aspects of water to some extent. We could put in a rain gauge, and we could watch to monitor and compare that with what's going on with the pore pressure. So these are the kinds of things that we can do. A tilt meter is another great one. So if you orient a meter into the ground and you hold it stable, and then as the ground moves and changes shape and changes its angle, the tilt meter will record that, so that we have an idea of whether or not it's a translational slide, a rotational slide, what's happening. So there's a lot we can do. All right, so monitoring active landslides. Surface signs include, in terms of detection, cracks or bulges in the ground surface. This would be a classic example. This is where we see a headscarp that's starting to form. Here's a geoscientist, a pair of them actually over here, or I'm sorry, yeah, there's two of them that are walking along that headscarp. This is actually a fairly dangerous place to be doing some work. Cracked concrete foundations, tilted trees, and other disturbances. These are all dead giveaways that you have some kind of land disturbance that's going on. Geologists can also monitor the underground by displacement instruments, which is what I just showed you in the previous slide. But some of the new stuff that we're doing is laser and radar surveys, photogrammetry, and satellite measurements, which also provide motion assessments of large areas. We can get extremely detailed measurements, very, very, very accurate measurements using lasers now, things that we couldn't do before, and it's much safer, and we can do it from a large distance. You don't actually have to be on the landslide anymore. And some of these radar surveys have actually been effective not only at detecting the existence of landslides, but in predicting when they would actually fail. And there's been several very successful landslide predictions that have been done in the Alps. The French and the Swiss and the Italians have gotten very good at certain areas and certain regions at monitoring for landslides. But unfortunately, they can't watch all of the Alps, so they look at very specific target areas that might pose significant risk to people. We have a long way to go in the technology. And that's kind of shown by what we see here. This is an image of landslides in Hokkaido, Japan. This is after an earthquake that occurred in 2018. This is an incredibly destructive set of landslides. There were many people that lost their lives in this location. And this is a group of islands. This is a group of people that live on these islands right here on Hokkaido that are very wealthy. They have all of the slope management technology, and still they didn't detect it. This was an earthquake-triggered landslide event that came off this slope here. These are volcanic deposits that came down here that this is all made out of. And effectively, the trees and all this debris came down into this landslide and killed the people that live over here. And this was actually a widespread slide. This is just a very, very small part of it. It was all over the place. And it's one of those things that it's one of the most haunting photos that you could see, seeing these places where people used to live and where people are now dead, in a place where they're very wealthy, they're used to landslides, they're used to earthquakes, and they still weren't able to predict the type of outcome that would happen here. Landslides will forever be a major problem as long as we have earthquakes, flooding, or any of these other things on Earth. It'll be working in conjunction with these things to trigger landslides. All right, well, thank you for getting all the way through with me, joining with me on this landslide video and talking about mass wasting. Rocks have to make their way back to the ocean, and the way that they make their way back to the ocean is through the river system. So my very next video is going to be a video on rivers and waterfalls, and I hope that you're going to join me for it. If you have any questions about landslides or mass wasting, or you're just generally excited about it, please drop a note in the comments, and I look forward to reading them. I hope you guys are all doing well, and we'll see you in the next video. Take care.